In this part, we will talk about CPU scheduling algorithms. The algorithms we will look at are first come first serve, shortest job first, and shortest remaining time first algorithms. So the first come first serve algorithm is simple, but it is not very suitable for systems that rely on time sharing. So for example, if we have multiple processes that are doing a time sharing for a CPU, then the first come first serve algorithm doesn't do a good job. And we'll take a look at examples where we show that. The next algorithm is shortest job first, SJF. It performs very well, but it is purely theoretical, and it relies on a prediction of burst time. So we can approximate shortest job first algorithm if we have a good prediction algorithm in place for burst times. The last algorithm over here is shortest remaining time first, which is a practical approximation to the shortest job first. Because shortest remaining time first doesn't need to do a prediction of burst time. It is going to rely on how much time remains in a particular process execution. So we'll take a look at all three of them with examples. So we start with first come first serve scheduling. As I said, it's the simplest CPU scheduling algorithm, and it essentially works on the principle that you request the CPU first, you get the CPU first. So it is going to be independent of the priority of the process. It is going to be independent of the burst time of the process. It is essentially going to depend on the arrival time of the process into the ready queue. So whoever comes there first gets the CPU first. The implementation is managed using a first in first out queue. As you can see over here, there's a queue of processes. All the way to the right is the head of the queue, all the way to the left is the tail of the queue, and the processes are essentially entering from the tail, and the CPU works on the process that is at the head of the queue. So when a process enters the ready queue, the process control block of that process is linked to the tail of the queue. That's how it enters the FIFO queue. And when a CPU is free and ready to take on processes, then the CPU is allocated to the process at the head of the queue. And once the execution is complete, then that particular process is removed from the head of the queue, and everything moves from left to right, one process up. So that's how we schedule the processes on a CPU using the first come first serve algorithm. Let's take a numerical example to show some deficiencies in this algorithm. Let's suppose there are three processes, P1, P2, P3. They are coming into the ready queue. Let's say P1 comes first, then P2, then P3 comes into the ready queue. So their arrival times are staggered a little bit, but in that order, P1, P2, P3. And their burst times are given to us. For example, P1 has a burst time of 24 millisecond. What that means is the CPU is going to have to allocate the 24 milliseconds of its time to complete process 1. And similarly, P2 has a CPU burst time of 3 milliseconds. P3 also has a burst time of 3 milliseconds. So because we are using first come first serve, and because P1 comes first, that is the process that we are going to allocate to the CPU first. So waiting time for process 1 is 0. It didn't have to wait. When it came, say the arrival time is 0, it got the CPU right away. It didn't have to wait at all. It ran for 24 milliseconds without any interruptions. So that's another thing with first come first serve. No preemption. So no stopping P1 until it finishes. So for 24 millisecond it continuous, P1 gets executed. Then because P2 came next, the P2 is going to get the CPU allocated to it. But it had to wait for 24 milliseconds to get that. So waiting time for process P2 is going to be 24 milliseconds. It is going to run for 3 milliseconds without any interruptions, and then P3, because it came last, it is going to start after waiting for 27 milliseconds and is going to run for 3 milliseconds again. So if we wanted to find the average waiting time, we can essentially do a average of the three waiting times that we just computed. So the average waiting time, and this is to begin processing of those P1, P2, P3 processes, is going to be the average of 0, 24 milliseconds, and 27 milliseconds. So we compute the average, and it turns out that the average waiting time, if we get the processes in that order, P1, P2, P3, is 17 milliseconds. Now, what would be the average time if the processes arrive in a different order? For example, what would happen if P2 came first, then P1, sorry, P2, then P3, then P1? So for example, if we put the longest process P1 way at the end, what would happen? Well, you can run through the simple math here, but you should observe a substantial reduction in average waiting time, which goes to show that if we use first come first serve scheduling algorithm, then the average waiting times will vary substantially if there are large variations in the process's CPU burst times. So that variations, the reason for that is because there is a big difference between P1 burst time and P2, P3 burst times. So it depends on the order in which the processes arrive to the CPU, arrive to the ready queue, which is not a good thing. So we could have a really bad number, or we could have a really good number if we arrange them differently. That's not a consistent um, uh, way to do things. So that's a negative for the first come first serve. And another negative for first come first serve is that it is a non-preemptive scheduling algorithm, which means that if process 1 is running for 24 milliseconds, we are not going to be able to stop it. We are not going to be able to preempt it. So that's another disadvantage. And if it is right at the front, it is going to hog up the resources for a long time. Next, we look at the shortest job first scheduling algorithm. This is exactly the same as first come first serve. However, we are right now scheduling the shortest job first. So say P2 was the shortest job, 3 milliseconds, then P3, then P1. So if we somehow know how long each burst will be ahead of time based on some sort of a prediction, then we assign, or then we put P1 right in the front, then P3, then we will work on the longest process. So by now you must have figured out that the shortest job first scheduling algorithm requires prediction to be made. So it's purely theoretical, but we can get some approximation done by using exponential prediction. So, and we'll take a look at that as well. So what would happen to the average wait time in this case? P2 comes in, waits for no time, gets the CPU, works for it for 3 milliseconds, waiting time for P2 is 0. Didn't have to wait at all. P3 had to wait for 3 milliseconds because the processor was working on P2, so waiting time for P3 is 3 milliseconds. P1 waited for 6 milliseconds in order for P2 and P3 to finish. So the waiting time for P1 is 6 milliseconds. The average waiting time, the same way we computed the average waiting time earlier, is now 3 milliseconds. So it's a very big reduction in the average waiting time. But as pointed out earlier, we require a prediction, ahead of time knowledge of the burst times. So let's see how we can predict burst times. Shortest job first, it is going to be impossible to do exactly because it's going to be it is purely theoretical. So let's see if we can implement an approximation. So we are going to take a look at the recent history of burst times, and we are going to hope that the trend will continue. And we will see an equation over here, and the equation is simply to calculate the predicted value of the burst time for the next event, and the predicted value is calculated by scaling the previous measured or previous actual value and the previous prediction value. So we are essentially taking the two previous measurements of burst time. One is the actual one or the measured one, and one is the predicted one. And we are scaling them using a factor alpha. So alpha times whatever was measured, 1 minus alpha times whatever was previous predicted. And alpha is between 0 and 1. So we can have a very high weight for prediction, or we can have a very low weight for the previous prediction. And depending on the two previous values and the choice of alpha, we are going to get the predicted value for the one time step ahead. The initial value, so clearly we need an initial value for previous prediction. So the initial value for previous prediction is going to be a matter of choice, and it is going to be a fixed default constant. The previous measured value is denoted by letter T for measured and n minus 1 because it was previous, one step time step before. The previous prediction value is tau for prediction, and n minus 1 is because it's the previous time step. And the previous just the predicted value for the burst time for a particular process is going to be tau for predicted, and n because it is for the next time step. So tau is being used in relationship with predictions, and t is being used in relationship to the measured times or the actual times. This is called exponential averaging, and we can write this algorithm again over here essentially. So if we let Tn, T is for actual or measured, so let Tn be the actual length of the nth CPU burst for a particular process, then we are going to define the predicted value for n plus 1, the next time step, as the predicted value for the next CPU burst. Alpha, let that be a factor between 0 and 1. So we have the equation tau n plus 1. So the predicted value of the CPU burst time for the time step n plus 1 equals alpha scaled with, the scaling factor is alpha for the measured or the actual value of the nth CPU burst time added with 1 minus alpha multiplied by predicted value of the nth CPU burst time. And as we can change the value of alpha between 0 and 1, there are going to be two edge cases or two extreme cases. When alpha is 0, this particular term will go to 0, which means that our prediction will entirely depend on the previous predicted value. So tau n plus 1 equals tau sub n. That means the recent history doesn't count. So the recent history of the measured value doesn't count. We are solely basing this on predictions, which is not a good choice. And if we go to the other extreme where we have alpha to be 1, in this case we make the prediction go to 0, and then our next predicted value is going to be completely dependent on the previous CPU burst time. So in this case we make sure that our next CPU burst or predicted CPU burst is the same as the previous one. So only the last actual CPU burst counts in this case, which is not good either, because now it is going to, there's no benefit, there is not real benefit of prediction. So there's no history, there's no memory involved. it is only looking at the previous one time step. So that's not good either. So the extreme cases don't work very well. Perhaps a value in the middle where we split half predicted, half measured, sorry, half predicted here, half measured there, then we perhaps can see a prediction algorithm working better. So let's see that in this graph. Here we have an example with alpha set to half, tau sub 0, so that is our initial predicted value for the CPU burst time as 10. So if on the x-axis we have time, on the y-axis we have the CPU burst times. And as you can see, there are two lines over here. One is for the predicted CPU burst times, the blue line, and the black line is the actual CPU burst time. And both, so because we chose the initial predicted value to be 10, the blue line starts with 10, but the actual one is at 6. So let's see what happens at time step 1. So that's the first grid line here. So at the first grid line, we are going to scale our value, predicted value that we obtain over here. Half of it is going to be with the actual value 6, and half of it is going to be the predicted earlier value 10. So half of 10 is 5, half of 6 is 3, we add those up to get 8, and that's how we are getting that value 8 for predicted value for time step 1. And if you keep doing this, you can see that the blue line closely follows or somewhat follows the black line, which is the actual CPU burst size, denoted by T sub I. So over here we can play with the value alpha, the parameter alpha, to increase or decrease our dependence on the previous values or the history. And we can also play a little bit with the initial predicted value, perhaps by looking at the history of the process. So that's a prediction algorithm working, an example of how a prediction algorithm works. As you can see over here, between this and this time step, there is a big jump from 4 to more than 12. The prediction algorithm doesn't react to it very quickly because we are just basing that on half of the previous two values. It is going to slowly reach there. So that's a consequence of choosing this to be half. If we want that to reach there very quickly, then we want to make sure that our history or the dependence on the actual value 13 here is more. So by doing that, we quickly reach there. But then, of course, there are disadvantages of doing that as well. All right, so I hope this gives you a good idea about how that prediction exponential averaging is working. Essentially, there's a moving average or the exponential moving average filter, essentially. Okay, let's now talk about two different types of scheduling, preemptive and non-preemptive algorithms. So non-preemptive algorithms are those in which a new process can be dispatched only when a process terminates or switches to the waiting state. So the scheduler dispatch can only assign a CPU to a process, a new process, when the old one got terminated or it got switched to a waiting state. So non-preemptive is, I'm not going to disturb the process that is currently running on the CPU. Which is the case, for example, with the first come, first serve scheduling algorithm. It's a non-preemptive algorithm. Preemptive algorithms are a little bit more real, more useful, and the actual, say, Linux operating system uses a preemptive priority scheduling algorithm. And we'll talk about priority scheduling later on. But that's a preemptive algorithm that works on Linux. So what is a preemptive algorithm? Well, a running process may be preempted by another process. So essentially removed from the running state and put back into the ready state. It can be preempted by another process based on some criteria. It might be because of the priority, it might be because of the time that is remaining, it could be dependent on a variety of criteria. But depending on those, it will be preempted by another process. So this will make sure that there is some sort of fairness that we can use, and not one process can just hog up all the CPU resources. But preemptive algorithm is going to be a little bit more complex because we are going to have to manage that criteria and preempt processes on a regular basis. Next, we look at the shortest remaining time first algorithm. This is SRTF, which is a practical approximation to the shortest job first scheduling algorithm. So when a new process arrives or a burst is complete, then we look at the time remaining estimates, TR, for all the processes that still need the CPU's attention, and we schedule the one with the smallest time remaining. So this will hopefully be clear when we work through this example. So this is for shortest remaining time first. We have 4 processes, P1, P2, P3, P4. Their time of arrival to the ready queue is listed as 0, 1, 2, 3 milliseconds each. So P1 comes in first, then P2, then P3, then P4. And their estimated burst times are given as 8 milliseconds, 4 and 9 and 5 respectively. So clearly P3 is the longest process, P1 is long 2, the shortest process over here is P2. So how are things going to work? Well, at time 0, clearly P1 arrives, there's nothing else in the ready queue, so P1 arrives and gets the CPU's attention. So it's going to start executing then. So for 1 millisecond, it is going to run. And at 1 millisecond, we are going to get P2 come in. So at 1 millisecond, P2 arrives with time remaining 4 milliseconds for P2. P1's time remaining went down from 8 milliseconds by 1 millisecond to 7 milliseconds. So what is going to happen at time step 1 or time unit 1? In this case, it is 1 millisecond. What is going to happen? Well, the CPU is going to have to preempt P1 so that P2, which is right now having a shorter time remaining, 4 milliseconds, so the CPU will be assigned to P2 next. So P2 will start running, and it will do that for 4 milliseconds. Now, a few things went on in the middle. P3 came in, P4 came in. Let us see what happened there. So at 2 milliseconds, P3 arrives with a time remaining of 9 milliseconds, all of it. And at that moment, P2's time remaining was 3 milliseconds. So P3 had to wait. Similar thing for 3 milliseconds. At 3 milliseconds, P4 arrives with a time remaining of 5 milliseconds. At that time, P2's time remaining is 2 milliseconds. So P4 also will have to wait. So no more new processes are coming in. At 5 milliseconds, which is essentially after you remove this one, all of the 4 milliseconds burst time for P2 are complete. So this yellow down arrow is indicating that P2 has completed and it is now going to exit to the terminated state. So P2 finishes at that time. Now we have a few remaining processes to complete. P1 is remaining, P3 is remaining, P4 is remaining. So what is going to happen at 5 milliseconds? P2 already finished. P1 time remaining was at 7 milliseconds. P3's time remaining was 9 milliseconds. We didn't get to work on P3 at all. P4's time remaining is 5 milliseconds. We didn't work on P4 at all. So the shortest time remaining is of P4, so P4 will start and it will run for 10 until 10 milliseconds, for a total of 5 milliseconds, because during that time P4 will continue to go smaller and smaller. So 5 will become 4, 3, 2, 1, 0, and it will be the shortest time remaining, because P1 and P3 will have longer than that. So P4 will finish at 10 milliseconds. At 10 milliseconds, we are going to have to make a choice between P1 and P3. P1's time remaining is 7, P3's time remaining is 9. So P1, because it has shortest remaining time, it will resume. It goes back to from the ready state to the running state, or gets the CPU processor, and it will work for 7 milliseconds. It will finish at 17 milliseconds, and then we will work on P3 next, because that's the only process remaining. So we'll work on P3 last. So actually P3 turns out the longest process over here got the CPU's attention last, and it finished at 26 milliseconds. So that's how we work through this problem, where we have different processes that are arriving at the ready queue at different times, and their burst times also are a variable. So next we are going to look at a Gantt chart. So we are going to see whether we can express or show what the CPU was doing at what time. And we do that by using a Gantt chart. So this particular picture that you see over here is from the previous slide that we did, and the highlighted time marks are the time marks at which there was a switch from one process to another process. So at 1 millisecond, we moved the CPU, stopped working on P1 and started working on process 2, and so on. So 1, 5, 10, 17, and 26 have been highlighted. And that data is also captured in this table, where the top row is time in milliseconds and the bottom row is process. So process P1 worked for the first time unit until 1, process 2 worked until 5, so 1 to 5 P2 was working, 5 to 10 P4 was working, 10 to 17 P1 was working, 17 to 26 milliseconds P3 was being run on the CPU. So these are two charts, those are called Gantt charts, that gives us a good idea about how the CPU time was managed in this SRTF algorithm. So with this you can compute your waiting times and the other times, for example turnaround time and so on, by using their definitions. All right, so in the next lecture we will start talking about how we can schedule priority into these scheduling algorithms. So that's for the next part.